Okay, here we go with question number 9. Okay, as ever, I'd like you to try the question first, just to make sure you kind of know what's going on here, and then have a look at the answers when you get a chance to. Okay, please do have the question in front of you so you're not just looking at the screen. It really does help if you're being active whilst doing this. So, having said that, let's go through the answers, right? Let's look at first. This is a common one that I've noticed in recent papers. Vectors really do not play a huge part in the GCSE, especially coordinated sciences curriculum. They seem to just be asking a little bit more. Okay, so you need to be aware that vectors are quantities which have direction and size. All right, so in this case, two examples would be acceleration and weight. Now, in the case of weight, it's probably quite a good one. Weight is a force. Now, forces push and pull. They can be up or down. In this case, weight always acts towards the center. And so you notice it has a direction. The weight always acts down. If it has a direction, therefore it is a vector, and therefore we can circle it here. Acceleration is another one. If you have an acceleration up, an acceleration down, then that would be an example. The ones that are not vectors would be speed. Speed is just stated as meters per second. You don't have a direction up or down, left or right. Temperature certainly doesn't, even though it can be positive or negative, doesn't mean you're going up or down. And time, well, can we travel backwards in time? Let's just say no for now, or that's an interesting debate, okay? Again, in this case, I have noticed that CIE is doing this more and more. I would say that they are being quite restricted in terms of what they're looking at. One which is not included is one called displacement. Displacement is a vector quantity which you'd learn about at A level or IB level. It's not included here, so don't worry about that one. Okay. Now, of a more sort of attainable and easy kind of bit is our speed time graphs. Okay, let's just remind ourselves before we do any questions about speed time graphs. Speed time graphs are useful for three things. Obviously, they tell you the speed. Fantastic. We can describe the motion of the car. We can also determine the acceleration from here, so we can know that we are changing speed. It gives us the gradient of that line. So the gradient here is the acceleration. You notice here we've got a non-zero, zero, deceleration and a deceleration and another zero acceleration here. We can also get the distance. Very commonly asked questions. Calculate the distance. You need to calculate the area under the graph. So that involves calculating the triangles or the rectangles depending on what shape it is you're looking at. Okay, so let's see the question. We'll go from there. Nice one. Describing. Okay, describing the motion of the car between 250 seconds and 375. This is describe. I've circled the word describe because obviously it's a command term here, but I know that students struggle with this question. Why? It's not a particularly difficult one. It's the fact that you have to describe and not explain. Students are really good. They love explaining things. They love telling us that the car has got a thrust or it's using chemical energy from its engine, etc., etc. We are not interested in that. We want to describe it. So what are we going to do here? Well, we're going between 250 and 375. So if you describe anything over here, that's pointless. We only are interested in this bit. In 250 to 300, the car is traveling with constant speed. Zero acceleration. That's all we need in there. We then have the second mark there. Car slows down with constant deceleration. That's it. You could say the word acceleration here, by the way, that'd be fine as well. Accelerations and deceleration are essentially the same thing. One of them is positive and one of them is negative. That's all you need in here, nothing else. Okay, we're then being asked to calculate the acceleration in the first 40 seconds. As we said, that's the gradient of the graph. We're going to go 20. Okay, we're going 40 seconds, so we're expecting 20 over 40. Nice, easy number. Okay, and that's our acceleration here. Now, you notice here it says state the unit. So this is why this is a 3-mark question, okay? Just be aware of the fact that, again, increasingly, CIE likes to ask 3-mark calculations. Usually it's 2 marks for the actual calculation. So if it was a normal one, this would get you 2 marks. The third mark comes from the units. You can write the units in 2 ways, meters per second squared with the 2 up at the top, or meters per second, the change of speed per unit time. So just pay attention to that. Anytime you have a question, calculation you need to do, check the number of marks, because that could give you an indication of the amount of work you've got to do. Okay, we're then asked to describe energy changes. This is not one that I've seen that much, so again, it's one to pay attention to, especially if this is a new style of paper. We're being asked to complete the sentence to describe the changes in energy stores when the car accelerates. Well, we're looking at energy stores decreasing and energy stores, the other energy store, kinetic energy. Let's see what we're doing. We are accelerating. So let's work backwards here. Accelerating means speed up. It means this amount of energy in the kinetic energy store is going to increase, half mv squared. If v is going up, kinetic energy is also going up. The bit that I think students might struggle with is where that energy comes from, and that comes from a chemical energy store. Okay, oil, which you assume is powering this car, is a chemical energy store, just like coal, just like food, just like batteries. And so therefore, when the chemical energy store goes down, the amount of energy in the kinetic store energy store goes up. So it's quite a nice question to test your understanding of types of energy stores. Finally, we've got the car is traveling at constant speed, and there are changes to other energies. Again, I've seen this in different forms, so it's clearly something that they're working on at CIE in terms of a skill. Well, we want to state the name of the energy stores and describe the changes. Well, in this case, we're still thinking about chemical. Remember, if you're driving a car, as long as the car is pushing along, it's going to be doing some work. That energy has to come out from somewhere. It comes from chemical energy. And that chemical energy is still decreasing. So this is a bit of a freebie here because it's the same as in the previous question. However, the thermal store increases. Now, what does that mean? When we're going at a constant speed, you would expect the speed to go up, but the speed here is constant, so the energy has to go somewhere. It's not going into your kinetic energy store. It's not increasing the kinetic energy store. It has to go somewhere. What it's going into is in the surroundings. When the car is traveling, it's being slowed down by something. Could be friction, could be air resistance. And in both cases, you're causing the transfer of thermal energy to the surroundings, so to the road or to the air, which is around the object as it moves. This is similar to when an object travels at terminal velocity, when a parachute is falling. Okay, when the person stops accelerating, then the steep keep on going down, that GP is going down, kinetic energy is not going up, energy goes somewhere, it goes to the surroundings.